présenter Pierre Salati, qui est professeur à l'université de Chambéry, qu'on nomme maintenant Savoie-Mont-Blanc.
Oui, voilà. Oui, oui.
Voilà. Alors, on se connaît avec Pierre depuis 1984, on ne compte plus les années. Hein. Il travaille au LAPTH, qui est à Annecy-Le-Vieux, et ses sujets de recherche, voilà, de prédilection concernent le domaine de l'astrophysique des particules, et plus précisément, il travaille sur les limites cosmologiques, sur les extensions au-delà du modèle standard de la physique des particules, donc la supersymétrie. Il a travaillé aussi sur la dynamique des amas globulaires, et puis beaucoup aussi sur le rayon cosmique, oui. Et puis sa relation avec la matière sombre. C'est le sujet sur lequel tu vas nous entretenir aujourd'hui. Oui, oui. Voilà. Merci, bienvenue à l'IAP.
Merci Elisabeth, c'est toujours un grand plaisir d'être avec vous. Should I speak English or is French okay? English, okay. Okay, good. Oh. So it's a great pleasure to be here. I consider IAP as one of my houses, my home, my second home after LAPTH in Annecy. And today, so I'm going to talk about dark matter in the light of cosmic rays. So I'm going, in fact, to present you the relations between those two fields. So I will, first of all, start by explaining why there is an interplay between the problem of dark matter and the study of cosmic rays. Since I was asked to be pedagogical, I will be very basic about cosmic rays, just reviewing a few properties of cosmic rays, and also what do we call dark matter. Then I will deal with a recap of what has been so far achieved between those two fields, in fact. It turns out that those two fields have nurtured each other, and that the search for dark matter particles has triggered some activity in the cosmic ray field and vice versa. So we'll see how, for instance, the discovery of a positron excess has triggered quite ferocious activity in the field of theoretical particle physics. And then I will end my talk by a few prospects and discussing the challenges ahead of us. Okay, so if you have one transparency, one slide to remember, this is the one which you need to keep in mind. So the rest, well, I hope that you will listen, but I want you really to look at that. So the relation between dark matter and cosmic rays is explained here. The point is that, well, we know that an important component of the universe called dark matter pervades galaxies, galaxy clusters, is present also on cosmological scales. And one of the major discoveries of WMAP and Planck is that the dark matter is non-baryonic. It's not made of ordinary matter. And so because of that, well, this discovery has, more, so to speak, justified the efforts made by the particle physics community to find a dark matter candidate. And it could well be, after all, that the dark matter is made of particles. So we will deal with which kind of candidate we have. But in principle, well, the dark matter could be made of weakly interacting massive particles that pervade, in fact, and are present everywhere, as in this room, for instance, but also in the galactic halo. So here is a representation of what could be our galaxy. And this galaxy is embedded inside a dark matter halo made of particles, of dark matter particles. And those dark matter particles, in fact, will we will steadily annihilate with each other. This does not jeopardize their population, but leads to the production of eventually standard model particles. And among them, anti-cosmic ray particles, which are very rare, as we will see, well, in a few slides. And the point is that, well, those antimatter particles, namely positrons, antiprotons, anti-deuterons, but also anti-helium-3, could be manufactured already by the interactions of primary cosmic rays, protons and helium nuclei, on the interstellar medium. So this reaction is typical of what is achieved, in fact, in accelerators. It's when you have a fixed target and you have a beam interacting. So you can imagine that this is just something that occurs on astrophysical scales in the disk of the Milky Way, producing antimatter particles. And if dark matter particles do exist and are present in the halo of the Milky Way, they will annihilate and produce those antimatter cosmic rays as well. And so all my talk will be, in fact, about those cosmic rays, how they are, how we can calculate the flux of those cosmic rays, and also on how we can model the production of antimatter particles by dark matter annihilation. And the idea, in fact, here is to try to find the dark matter under the form of those heavy species by a distortion, in fact, in the, for instance, here, antiproton flux at the Earth. And so if the dark matter is made of particles yet to be discovered at accelerators, then you can try to detect them through direct detection, through the collision of those dark matter species on a terrestrial detector, on the nuclei of that terrestrial detector. This is called direct detection. You can also try to produce them at accelerators at the LHC. And a third possibility called indirect detection is pictured here. You can try to, in fact, look for the distortions in the various fluxes of antimatter cosmic rays. So what do I call dark matter here? What we have in mind here is a quite particular dark matter candidate. We will work in the framework of the, so to speak, natural extensions of the standard model of particle physics, for instance, supersymmetry or extra dimensions, where the dark matter candidate arises naturally. It's a stable particle, so it has been manufactured in the early universe. It's stable because, well, it's protected against decay by some conservation of some quantum number. And it's a particle with a mass between, say, a few GeV, a few TeV, but we can generalize that, and the dark matter particle will be a particle with a species with a mass between, say, a few MeV and a few TeV. And the prototypical example, in fact, of the behavior of that particle in the early universe has been worked out by Russian people and also by these two physicists, Ben Lee and Steven Weinberg, in 1977. And what they showed was that when, in the early universe, well, the particles at very high temperatures are an ultra-relativistic radiation. And then the temperature drops below their mass, they start to annihilate. And at some point, well, the annihilation stops because the density is so small that the probability for one particle to find a partner upon which it could annihilate, that probability starts to be less than 100% when computed on a typical expansion time of the universe. So in other words, well, as soon as the annihilation rate, which depends on the density of the dark matter particle, becomes less than the expansion rate, the density is frozen. And here are typical calculations of the codensity, the density, well, the number of particles per expanding volume in the expanding universe. And you can see that when the temperature here drops below some value, then the density drops and then stabilizes. And a major discovery, in fact, is that the relic abundance, the density today of those species, does not depend on their mass, but just is inversely proportional to the annihilation cross-section. And this was not noted at the time, but it turns out that with that value of the cross-section, with an annihilation cross-section of 3 times 10 to the minus 26 cc per second, you end up with a relic abundance of any of those particles with weak interactions that are massive, but the mass is not that important here, as we've seen. You have a relic abundance which matches actually the Planck measurement. So that is quite miraculous. It's called the WIMP miracle. And so it has triggered people to think that, well, it's not that miraculous, but maybe, well, it justifies the fact that the WIMP are really a natural candidate. Well, okay, so there are many other possibilities, in fact, to cook up this relic abundance. So there have been extensions of that with co-annihilation when you have two species in the early universe. So actually my PhD thesis was about co-annihilation in the 80s. You also have not freeze out. The process which I showed you is freeze out, but you could have freezing. For instance, you can imagine after the inflation, the plasma is reheated and generates just by mere interactions that density. So the density, instead of dropping down from a constant level, increases because it's created from a medium that is reheated. You could also have bound states anyway. So this is the framework in which we are interested and in which we are going to study the relations with cosmic rays and with the production of antimatter cosmic ray species. A candidate that was not that fashionable 20 years ago, but that has come to be quite looked at today, that candidate is primordial black holes. You can imagine that you have evaporating primordial black holes, and those evaporating black holes could actually generate antimatter particles. We've written a few papers on that. Okay, so as regards cosmic rays, a few basic observations. So I apologize because this is very naive, but anyway. So the cosmic ray density with which people is working is d n over dE. It's the number of cosmic rays per unit volume per unit of energy. And you can work out the flux, and the flux of cosmic rays is always given as a function of d n over dE as 1 over 4 pi v psi. So these are just definitions. Okay. A few basic observations now. It turns out that cosmic rays are quite isotropic. What we detect on Earth orbit seems to be very isotropic. And the cosmic ray flux, which is detected, is a power law on many decades. So that's very, very interesting. It's presumably related to the way those cosmic rays are accelerated. And most of the cosmic rays are protons. It's 90% of them are protons. 10% of them are helium nuclei. You have just a percent mixture of heavy nuclei. Then electrons, well, comprise 1% of the cosmic rays. Then positrons, 1 per mil. And then antiprotons are in a fraction with respect to protons of 10 to the minus 4. And you can see here that the spectrum is really a power law. There are, though, some breaks around the PeV region and here. So there is the knee. There are even 2 knees, in fact, and here is the ankle somewhere at 10 to the 18 electron volts. And another important information is that, well, the abundance of cosmic rays, the abundance of the various elements in cosmic rays matches very well the abundance, in fact, found in the solar system, except for the lithium, beryllium, and boron, and some sub-Aryan elements. And this has led people actually to work out the propagation of cosmic rays. So we do believe that, in fact, for instance, protons and helium nuclei are accelerated. There are elements inside the interstellar medium that are accelerated by supernova-driven shock waves. But lithium, beryllium, and boron, which are not in the interstellar material, are produced by the fragmentation of carbon, nitrogen, and oxygen. And so this has important consequences about how we can actually model the propagation of cosmic rays. Just to flash you this very rapidly, the first models, in fact, were very, very basic. The disk of the Milky Way was pictured as just one box. And for instance, the carbon nuclei here, which are primary nuclei, are produced with the rate Q of C, then they could be destroyed. In this very simple model, you can imagine that you have carbon nuclei that are accelerated, and then those carbon nuclei propagate in the box, that region where cosmic rays are confined. The carbon interacts on the hydrogen of the interstellar material to give boron. So here is the rate of that interaction. And they also escape with a typical time scale, which is tau escape. Or they just disappear, in fact, because it's not the leaky box, it's just the disappearing, the magic box, where the cosmic rays disappear. Boron is generated, in fact, by the interaction of carbon. And in fact, well, you can very well work out the boron over carbon ratio. And you see at once that the boron over carbon ratio is just given by that per section here, the density in the interstellar material, and that escape time. And that escape time, in fact, refers to how the cosmic rays propagate. So this is the Poolman model for cosmic rays, but, well, it already points towards something which is very important. In other words, the escape time, or the residence time of cosmic rays inside the box, we can imagine that boron and carbon have the same residence time, is just given by the boron over carbon ratio times 10 megayears. And measuring basically the boron over carbon ratio tells us what, in fact, the escape time is. So that's very basic, and when you do so, you realize that the B over C is of order at most, well, 30%, but 30% means that, in fact, the escape time is, for a few GeV in this region, is of order 3 megayears. So it tells you a lot. It tells you that, in fact, cosmic rays do not propagate ballistically, in fact, inside the disk, and they have to diffuse. And so that measurement, in fact, led people to cook out a diffusion model. So the propagation of cosmic rays, in fact, is just a mere diffusion process. And so, in fact, well, everybody nowadays, even those using GalProp, for instance, are going to use the model cooked up, invented by Ginzburg and Siravatsky, to ration. Here is a picture of Ginzburg. Just to give you a flavor of how discussing physics with him could be. And you have here, so here is a galaxy NGC 891, where the measurement has been performed of the synchrotron radiation here, and you have a map basically of the magnetic field. And so our galaxy, every galaxy, is presumably in fact surrounded by a magnetic halo. And the cosmic rays, which are the primary cosmic rays, which are accelerated inside the disk and will propagate inside the magnetic halo and will in fact diffuse on the magnetic inhomogeneities. Okay. And so in the game of cosmic ray physics, everyone is interested in solving that master equation. So it's a very simple equation. It's a diffusion equation, where psi was defined in the first slide. It's here. Psi is dN over dE. And what you have here is a diffusion equation that takes into account the diffusion process. You might have some convective wind that blows upwards and downwards with respect to the disk, which comes from the fact that the plasma, in fact, is accelerated by the stellar winds. And then you have also energy losses. You have some diffusion in energy that comes from the fact that the diffusion centers, the knots of the turbulence of the magnetic field, move, in fact. And so because they move, you have sort of a second-order diffusion mechanism, Fermi acceleration mechanism. Q is the production, and here is the destruction term on the interstellar material. And Q is either for primaries acceleration. You could have also secondaries, such as lithium, beryllium, boron, which are produced by primary destruction, primary cosmic rays destroyed on the interstellar material. And you also have here Q dark matter. And here is the connection with dark matter that comes here. Okay, and so nowadays, to solve that equation, either you have fully numerical codes. The most famous is GalProp, then Dragon, and you have now Picard. Or you could use, actually, in fact, a semi-analytic code, such as Usine, which we are using, actually, in our group in Annecy. And there is the bone code, which is based, in fact, on the calculations we did 20 years ago. And, in fact, every code has its advantages. This depends on what you want to do. So you can either use a bulldozer or a screwdriver. Sometimes, well, they don't do the same thing, in fact. So I'm not going to discuss the respective merits of each model. Okay. So after having discussed the relations between, in fact, cosmic rays and dark matter, in other words, well, the search for distortions in the cosmic ray fluxes or and antimatter cosmic ray fluxes generated by dark matter annihilation, on which you can superimpose, in fact, already the actual production of antimatter cosmic rays by interactions of primary protons on the interstellar material. Now I'm going, in fact, to present you a brief review of what has been achieved, in fact, as regards the relations between those two fields. Those two fields have nurtured each other, and that has been quite interesting. So even though we are not quite interested, in fact, here in gamma rays, because my main concern will be charged antimatter cosmic rays, I will just discuss very briefly, in fact, the importance of gamma ray observations. There are a few experiments, such as S trying, and Fermi-LAPTH as well, of course, trying to detect the emission of gamma rays from dwarf spheroidals. Dwarf spheroidal galaxies are known to contain a lot of dark matter, and so there are actually very nice probes, in fact, for the search of gamma rays through always the annihilation of dark matter species, which could generate gamma rays. And well, there is a nice relation between galactic dynamics, in fact, and those gamma ray searchers, because here, for instance, there is a very nice paper by Bonnivard, David Morin, and Céline Combet, the Grenoble group, where they have taken the observations of a few dwarf spheroidal, which are showed here, and they have used the measurements of the surface brightness, of the profile of the surface brightness, the profile of the velocity dispersion along the line of sight, here, sigma p squared, and they've used a Monte Carlo search where they have modeled actually the ellipsoid of velocities with beta, the anisotropy of the velocity ellipsoid. Nu of r is the density of stars, the number density of stars, and the trick here was to in fact, explore the dynamics of those dwarf spheroidals much better than before in order to compute a very important ingredient in that game, which is the J factor. The J factor, which, to which, in fact, the gamma ray flux arising from dark matter annihilation is proportional to. That J factor is the integral along the line of sight through the dwarf spheroidal of the square of the dark matter density. And so for the first time, in fact, that group has worked out the J factor quite properly through that Monte Carlo analysis, and has showed the uncertainties, in fact, on the J factor. And so you can see that actually it's very interesting. I found that it's a very nice illustration of the fact that, well, the gamma ray searchers for the dark matter presence inside dwarf spheroidal could actually trigger work in galactic dynamics and trying to understand and to model the dwarf spheroidals. Okay, so that was the first example. The second example is really the prototypical, in my opinion. In 2008, the Pamela satellite just discovered, or at least, well, established very firmly the presence of what was called at the time the positron excess. So here is the positron fraction, the flux of positrons over the flux of positrons plus electrons. And here is this yellow, this banana here is the band where you would expect the flux of that fraction to lie, should you have only, in fact, production of positrons through interactions of high-energy cosmic ray protons and helium nuclei on the interstellar material. So the yellow band here is just, in fact, the theoretical prediction for secondary positrons, and that band here encompasses the uncertainty on the cosmic ray parameters in the Ginzburg and Sierawetsky model arising from the Bronov-Carbon ratio. At the times then, the Bronov-Carbon ratio was not as well measured as today with measurements by AMS. And you had a large uncertainty. But nevertheless, although you had a large uncertainty, you can see here that the red points are much above, in fact, the secondary production. And so there was an evidence for primary positrons. And I can tell you that, well, maybe in the astrophysics community that was, well, not very exciting, but for particle physicists, that was thought at the time, 10 years ago, as the smoking gun for the presence of WIMPs inside the halo, annihilating into positrons. Those positrons, in fact, propagating and adding to the secondary production. And so there has been a bunch of studies, in fact, many analyses, very interesting ones. Well, and what we can say is that, well, that discovery of that excess, of what was called an excess, of course, has nurtured, in fact, the theoreticians in particle physics and has triggered a quite hectic activity, in fact, in modeling. And it was clear at the time that already it was very difficult, in fact, to have that excess explained just by standard dark matter species, because we know what the density is around the Earth, basically 0.3, 0.4 GeV per cubic centimeter. We've seen that if you want to have a dark matter relic abundance matching the Planck value, you need to have a cross-section of order 3 times 10 to the minus 26 cc per second. And we know that high-energy positrons do not come from far away, because as they propagate, they lose energy. And so if you detect, in fact, high-energy positrons, they must come from not far away. They must come from the local region. And so already at the time, it was clear that one had to increase, in fact, the annihilation cross-section. And to increase the annihilation cross-section, people invented, in fact, Prosper Laffan, basically, and his collaborators, and then Arkani Ahmed in Princeton, invented or resurrected, in fact, the Sommerfeld enhancement. The idea was that, well, you have a particle chi that might interact with a particle phi, which is a scalar or maybe a vector, which has a mass, a quite small mass, in fact, not to produce antiprotons. Yes, another problem was that, of course, well, when you have annihilation and production of many positrons, you don't want to have antiprotons at the same time, because you don't have an antiproton excess. You had just a positron excess. So the idea was to cook up a model that would not generate an antiproton excess, but would generate a positron excess with the right cross-section. And so with that kind of model, you can see that the particle chi annihilates into a phi particle whose mass is less than 100 MeV, and the phi decays into electron pairs. And so there was this idea floating around of secluded dark matter, or this is called secluded dark matter, where you have annihilation of chi particles into 2 phis, which subsequently, in fact, decay, and you will have 2 electron-positron pairs. Okay, and so you need to match. Well, you need to have, if you have a coupling with a constant alpha, the velocity beta is between those 2 values. And you might have, depending on the value of the mass of the mediator here, it's called also mediated dark matter, you might have peaks, in fact, in the annihilation cross-section. And so you could actually have, when the density, when the velocity is very large, when the temperature is very large, you have a cross-section that is normal. And this kind of process generates, in fact, a cross-section that is inversely proportional to the square or to the power 1 of the velocity. So you already have that, in fact. Just imagine that you have the sun and you have, in fact, a particle moving very fast. If the particle moves very fast, then the cross-section will be pi times the radius of the sun squared. But if the particle doesn't move very fast, its trajectory is bounded, and so the actual cross-section is enlarged. And so that's the idea in quantum mechanics, which was worked out by Sommerfeld. You had also, and nowadays, we are still working on that very bizarre idea that we might have a very large, huge dark matter concentration at the galactic center, producing, in fact, those mediators, which are actually long-lived and which could, in fact, deposit the positrons around the Earth. So just, well, this is an illustration, well, just to show you that actually there was a lot of excitement, and the field has been nurtured actually a lot from the discovery of that positron excess. So silly ideas, well, were proposed, and that is always very healthy, I think. Okay, so vice versa. In fact, there was also quite a lot of improvement also in the modeling of positrons. And so I'd like just briefly to mention that work, in fact, whose primary author, Mathieu Boudot, is in this room, where, in fact, the idea was to improve the calculations of the positrons from a semi-analytic point of view. You can always solve, in fact, numerically things, but it's always nice to do that semi-analytically because then you monitor the errors and you understand more what you have eventually. And so the idea is very simple. Positrons propagate, and they undergo Bremsstrahlung losses here in the disk, but in the halo and everywhere, in fact, there is a picture basically of the galactic disk. They can also have losses due to interactions on the CMB, on the cosmic microwave background, on stellar light. So they are going to lose energy through inverse Compton at high energy, and they are also going to lose energy through synchrotron radiation. And this paper proposed, in fact, to pinch the losses taking place everywhere in the magnetic halo, to pinch them, in fact, inside the disk. And by doing so, then it's possible to work out completely the equation, to solve it semi-analytically, and to have the spectrum all over, to have the spectrum all over the energy range, from MEV energies up to TeV energies. And you can see that, well, so far, people who used a semi-analytic calculation had that kind of flux here in dotted line, and when all the effects are taken into account, and especially diffusive reacceleration, you see that you have a bump, in fact, at a few GeV. And so dealing with those problems from a semi-analytic point of view, with a semi-analytic method, is interesting because it goes very fast, and you can actually do full scans and very important scans. And comprehensive scans. So, here, for instance, Boudot and his collaborators performed a scan where the positron flux is produced by a secondary component and by dark matter. And here, the dark matter can annihilate into a variety of different annihilation channels, a variety of particles. And so the idea was to try to fit the data, to fit the IMS data from sub-GeV up to several hundreds of GeV in energy. And so to see if it's possible to fit the data. And so here are the results of an extensive scan. So for each dark matter mass, so you can try to find the proper cross-section. So each dark matter mass is fixed, then we can take the specific cosmic ray models that survive, in fact, the boron-carbon ratio test and some other tests. I can talk later if you're interested. And also for various values of the Fiske potential. The Fiske potential controls what is called the solar modulation. The fact that, well, sub-GeV particles have a lot of problem to enter inside the heliosphere because they are repelled by the solar wind. Okay, and so here is the best chi-squared which we got, which is 1.5 per degree of freedom with a p-value of 0.4%. But you can see that the best fit which we have misses completely the 2 points which are here. And the message which I'd like to convey to you is that, well, we've shown, well, Boudot and his collaborators have shown in this paper, in this analysis, that it's not possible to explain the positron excess by just a secondary production and dark matter annihilation, whatever the annihilation cross-sections are, because the branching ratios were free to vary. So we need to have a third component, and as soon as we have a third component, we cannot say that the positron excess, well, is a smoking gun for the presence of WIMPs in the galactic halo. Too bad, but well, here is what it is. Very recently, so 2 years ago, the Dampé experiment. So I like very much the word Dampé because Dampé is a satellite on orbit sent by the Chinese. But Dampé is not Cosmic Ray Explorer, it's dark matter particle explorer. So you can see here it's another illustration of the ties between cosmic rays and dark matter. So that satellite was sent not to study the cosmic rays, but to look for dark matter and to look for the distortions and in the various fluxes. And so they have measured actually here the positrons or the leptons. No, I think it's the leptons. And they find out that in fact they have here in fact, okay, a break in fact. So you would expect to have a power law, but you don't have power laws. And you have here just in fact the flux. So the leptons is a generic word for electrons and positrons. And so here is the flux of electrons and positrons, and you can see that you have a cutoff. And so of course, well, if you have a dark matter particle, then you would actually expect to have such a cutoff because you see, well, you can't produce positrons or electrons with an energy that is larger than the mass of the WIMP. And so the fact that you have here a break in the spectrum and a cutoff here could be interpreted as also the presence of a dark matter particle. Is it? Well, in fact, no, because, well, 4 years ago, Joe Silk and Timur Delahaye and Cotera showed that, in fact, you would expect such a cutoff, either in the case of dark matter annihilating into E plus, E minus, mu plus, mu minus. So you take the green, the blue curve. But if you have actually a pulsar, a nearby pulsar, you also have such a cutoff. And the cutoff arises at high energy because the pulsar is so old that all the electrons and positrons that have been injected have lost energy and are confined, in fact, very high energies. And now the last item of that long list, in fact, but I find it interesting and to have so many items. Anyway, it's the the discovery of there are hints that there could be an antiproton excess, or at least, well, the discovery of an antiproton excess was advertised 3 years ago at CERN. So you see, well, 10 years ago it was the positron excess. Now, 3 years ago, people thought that there could be an antiproton excess. So I'm going to tell you that story. And there are some rumors that, well, even anti-helium-3 has been discovered in space. So I'm going just to deal with that. So antiprotons. So 3 years ago, basically, there was that meeting at CERN, so called the AMS Days at CERN, and the latest results from the AMS experiment on the International Space Station. And the first talk, well, in the first talk, that plot was showed, where you have the antiproton of a proton ratio here. So of course, well, those were preliminary results, but well, okay. And here was a node, actually, calculation of what is expected from second reproduction. So same thing as for positrons. You can, in fact, cook up antiprotons always by interactions of protons and helium nuclei on the interstellar material. So you have secondary antiprotons, and then you could have also production of antiprotons through the annihilation of dark matter. And so at CERN, well, this plot was showed, and you can see that it was quite a political slide, because then, well, you can see at once that, well, here is what expected, the second reproduction, and here is what expected, what has been measured. I forgot to tell you that for the positrons, there is indeed, of course, an excess with respect to the production of secondaries, but we know, and we always knew, in fact, not in the particle physics community, but you guys knew that in fact another important source of positrons are pulsars. And so a pulsar, a rotating pulsar, can actually, through its magnetic field, generate, in fact, electrons and positrons. And so the positron excess is just, in fact, the measurement of a flux arising from nearby pulsars, in fact, injecting electrons and positrons. This is not the case for antiprotons. If you have an excess with respect to a second reproduction, that starts to be a little problem, in fact. I don't know of any process that could generate antiprotons. Well, I can discuss that later, but you don't expect to have such an excess for antiprotons. Okay, so in fact, well, we redid the analysis. In fact, well, that analysis here is a very old analysis of us, which we published in 2008. And in 2015, we redid the analysis, and we showed actually that, well, the secondary expectation, in fact, lies somewhere on that band here, and there is no actually real reason to believe that there is an excess in antiprotons. So here is where we are. There are some claims, in fact, some refined analysis in last year, claiming that the Quoco, for instance, and collaborators claiming that, well, they could accommodate, in fact, a dark matter species. They couldn't find actually completely agreement between the secondary production of antiprotons and what was measured. And there has been a very recent analysis by the Bone group, by Winkler and collaborators, and Reinhardt, showing that actually as regards the antiprotons, there is no claim, no real claim of an excess with the dark matter. So here, in that game, what is very important is the fact that you have to work out the background, in fact. In other words, one has to work out the secondary production of antiprotons. It has to be understood very carefully. And what changed, in fact, in the calculation of that background was, first of all, that the fluxes of protons and helium nuclei was measured with better accuracy. There was also a recalculation, a remeasurement, in fact, or at least a new fit of the production cross-sections for PP going into antiprotons. And also the fact that, well, we realized that, in fact, in a PP collision, you tend to have more antineutrons than antiprotons. And just those three things, well, just popped up the background. Okay, as regards now the formation of antideutron, so antideutrons and anti-helium-3 are manufactured routinely, in fact, now at CERN, and were actually, by the way, back in the 60s in the Brookhaven National Lab in the US. And the idea is as follows. When you have an interaction of a proton with another proton, you might generate, in fact, antiprotons and antineutrons. And if these, in fact, have momenta which are close to each other, they will fuse. There will be fusion. There will be a coalescence. And so you can define, in fact, here, basically the probability to form an antideutron as the probability to generate an antiproton and an antineutron times some correlation C of delta. Delta is basically half the difference between the antiproton and antineutron momenta. And a very fashionable quantity is called the coalescence factor that tells you, in fact, that in fact controls the probability to form, in fact, an antideutron with respect to the probability to generate, in fact, an antiproton and antineutron, and you have that B2 factor. And that B2 factor is related somehow to basically the maximum difference between the momenta of the antiproton and antineutron. So really, you need to have the antiproton and antineutron in momentum space, which are very close to each other. And basically, as soon as the difference is larger than some value called the coalescence momentum, you don't form the antideutron. And this has triggered actually a lot of activity. You see, well, the interest in finding antimatter cosmic rays, anti-nuclei in the cosmic rays, has triggered activity in the particle physics community. Here is a recent paper a few months ago by the ALICE collaboration, where they have actually measured B2. And you can see that you have measurements of B2 here as a function of, well, the transverse momentum. You have to see here, what is interested for cosmic rays is the small pt, in fact, where most of the events take place. And so you have a measurement of B2, and also of anti-helium-3. So you can define the coalescence factor B of A for any, in the same way as for antideutrons, for any nucleus. And they have observed here on the left panel helium-3 and tritium, and on the right panel, the anti-helium-3 and anti-tritium. And they have measured, actually, the coalescence function. So it's measured at accelerators. And that measurement triggered, in fact, our colleagues from the Torino University to recalculate, in fact, here, for instance, the flux for anti-helium. Okay, so you have the secondary component here, the tertiary component arising from the anti-helium-3 colliding on the interstellar material, not being destroyed but losing energy. And you have here the dark matter signal here. And you can see that, well, basically, so everything depends, in fact, here on the coalescence function. You can see here that in that plot, one is very close to the sensitivity limit here on the right-hand side. So the extent of the bands, the width of the bands, comes from the bad determination of the coalescence function, of the coalescence momentum. It's comprised between 160 MeV and 248 MeV. Okay, and these are for two different models, in fact. On the left-hand side, one model which was compatible with, so to speak, sort of an antiproton excess. On the right-hand side, the MED model. Okay, so now prospects for the future, and so I will go faster because, well, ideas were clear as regards actually the way those two fields interacted, cosmic rays and dark matter. Now, what are the problems ahead of us? Okay, so a few remarks. So first of all, that idea to use galactic dynamics to infer actually informations about, say, for instance, the velocity dispersion of dark matter inside dwarf spheroidals or even inside our galaxy has triggered, for instance, Thomas Lacroix, who was here, postdoc with Joe here at IAP, Martin Streff and Julien Laval in Montpellier, to reinvestigate using a Dicton formula the velocity distribution, in fact, of dark matter species, and to use that Eddington inversion formula to get actually the velocity distribution of the dark matter species in order, well, okay, and as a function, in fact, of the density of matter. So rho is just the sum of the dark matter and the baryonic density. And this is very important when you want to set limits, in fact, on the annihilation cross-section when the annihilation is dominated by p-wave annihilation. When the annihilation is dominated by p-wave, the cross-section depends on the square of the velocity. So you need actually to know the velocity at every point in the galaxy. So there are results. I'm not going to show you the results. There will be, we're still working on that. Or at least, I mean, I'm discussing with my colleagues, but this is a project led by Mathieu Boudot, Martin Streff, Thomas Lacroix, and Julien Laval, and sometimes discussing with them. But I can refer actually to another work where we set limits, in fact, from this pinching method. We have a very nice method to compute the positron flux all over the spectrum of energy. And we can use, in fact, information on all the spectrum to infer limits, in fact, on the annihilation cross-section. And so here is, for instance, here are the limits of the annihilation cross-section as a function of the dark matter mass, well, set by positrons. Here is an example where, in the case where, in fact, the cross-section of annihilation is the thermal value, 3 times 10 to the minus 26 cubic centimeter per second. And you can see here, for instance, two different cases for propagation of cosmic rays. We imagine that we have a 10 MeV WIMP that annihilates into a line of 10 MeV electrons and 10 MeV positrons. And depending on whether in the blue case there is no, or there is in the green case, diffusive reacceleration, you can have, eventually you can compute the positron flux. And you can compare that with the AMS data and also with the Voyager data. So that's very amusing to have Voyager 1 that has exited the heliosphere, and you can start to use, in fact, the measurements performed. Okay. Another topic which will be very fashionable in the next years and which has become quite quite fashionable, is to use, in fact, also the gamma ray information in order to see how to explain, actually, to use the gamma ray observation to try to see if the positron excess is generated by positrons emitted by nearby pulsars. So here is, once again, the Dampé results for the leptons. For the lepton flux, here is the positron fraction measured by AMS, and here is Chinese analysis where the Dampé results are explained by the presence of two pulsars. So these are theoretical pulsars. It's not matching any observation. But we know, actually, that there are pulsars like Geminga, very close to the Earth, and it would be interesting to see, actually, if the positrons, the would-be positrons emitted by Geminga, which potentially could explain the positron excess, could be seen, in fact, in gamma rays at higher energies. And so, since time is running out, just one thing. It turns out that when you want to understand how positrons or electrons propagate in a medium where they diffuse and lose energy, so you need to solve that equation here, that equation above, the first one. And it boils down to the fact that eventually we receive at the Earth, we are here, we are surrounded by we are inside the magnetic halo, and we receive, in fact, positrons that come from a region, lambda d, which is given by that relation, which seems to be very complicated, but that's very simple. You emit a particle at very high energy, that particle diffuses and loses energy, and by the time it reaches the Earth, it has an energy E, whereas it was emitted at ES, and we can't receive, in fact, positrons produced at ES, arriving at the Earth at the energy E. We can't receive those positrons if they are emitted outside that sphere. It's just that the diffusion equation, in fact, boils down to a heat equation, blah, blah, and, well, okay. But that's very important, because then it tells you that, well, when you inject particles, then they tend to propagate, and by propagating, they lose energy. And so there was this night observation of Geminga here and some other source by the Oak Observatory, which is a terrestrial one in the mountains. And they have measured the gamma ray emission and quite far away from those sources, at tens of parsecs from those sources. And to make a long story short, the idea is that by measuring the gamma rays, the intensity of gamma rays, they can actually try to infer, they know basically what is the energy loss inside, around those sources for positrons and electrons. So you have electrons and positrons emitted by those sources that propagate in the medium, losing energy, and then, in fact, they observe photons with an energy of tens of TeV, or 10 TeV, 12 TeV, as far as I remember, generated by positrons with an energy of 100 TeV. And basically, well, they can work out what is the diffusion coefficient K gamma. That another analysis by Giacinti and Lopez-Cotto confirmed the first finding by the Oak experiment that the positrons and the electrons around those sources at 100 TeV propagate very slowly, diffuse very slowly with a very low diffusion coefficient. And that diffusion coefficient here, they computed at 100 TeV, is much less. It's 1, 2 to 3 orders of magnitude less than the diffusion coefficient inferred from the Brown-over-Carbon ratio, which actually is a problem. This has led, actually, and this is leading us to reanalyze things and to see, in fact, the diffusion inside the galaxy, as if actually, generally speaking, the cosmic rays diffuse, but sometimes they are trapped around those pulsar wind nebulae, where the diffusion, because the medium is probably shocked with a lot of turbulence, where the diffusion occurs very slowly, and there are pockets of very slow diffusion. So you see that, well, comparing actually what gamma rays have given us, well, gamma ray observations with cosmic observations have driven us, well, are driving us to this new picture. Another problem which I'm leaving to you, which I find it very interesting, is very theoretical. In all those analyses, we believe that the primary cosmic ray sources are homogeneously spread in space and time, but this is not so. We know that, in fact, cosmic rays are accelerated by shocks and by explosions. And those explosions are localized in space and time. And so it turns out that one must have some sort of a galactic variance arising from the fact that we don't know all the history in the Milky Way, and we don't know all the sources everywhere in the past 10 or 20 million years. And because of that, then you have some sort of galactic variance arising from the fact that, in fact, we know very little about the population, and when you switch from one population to another one, in fact, the flux of protons, of just primary protons, just changes. And you are led to some sort of a statistical analysis where, in fact, here, for instance, you would expect to have on average the red curve, but because, in fact, you have that galactic variance, you might have, in fact, a spread, and that spread is calculable, in fact. We thought that maybe we could explain actually why for the protons we have a kink at high energy, and we have a hardening of the spectrum of the protons at high energy that has been measured by AMS and been confirmed, or at least was already measured by CREAM, another experiment. And you can see that if we modify, for instance, the number of explosions per century, we have really a change here in the spread, and we could barely explain, in fact, the excess. Okay, so just a few things that are still open. It turns out that, well, you can define various lengths. The height of the magnetic halo is, for instance, in that example, 5 kiloparsecs. The Larmor radius is given by here the magnetic field. For 1 microgauss, it's 10 to the minus 6 parsecs. And the diffusion coefficient, which is always defined with lambda diff. Lambda diff is the typical length of diffusion. The typical length of diffusion is given here. And it turns out that when one scrutinizes the flux of cosmic rays, it's a power law, except it's a broken power law. You have here a softening at the knee, and you have a hardening at the ankle. And it's quite amusing to see that lambda diffusion becomes equal to the size of the magnetic halo box for precisely 10 to the 7 GeV, so basically somewhere here. And also the Larmor radius starts to be equal to the size of the box for an energy of 5 times 10 to the 9 GeV, so somewhere here. And so this raises the question to understand how we can model the diffusion when actually lambda diffusion starts to be large. In other words, well, there is a complete lack at the moment of an analytical description and understanding of the transition between diffusion and ballistic motion. So I think this is something which we need to understand. We can, of course, run simulations, but it would be nice to have that. And finally, well, cross-sections. We don't know actually what, there is a large uncertainty on cross-sections. All the work on the Brown-of-Carbon ratio rises from, in fact, and needs, in fact, needs a lot. Well, for instance, here the destruction cross-section for instance, boron. And here are the measurements here, and there are very few measurements with lots of uncertainties. And those uncertainties are really the limiting factor which we are encountering now in our group. We have a collaboration between Grenoble and Annecy, the Cosmic Ray Alpine collaboration, where we are trying to work out with David Morin and various collaborators using the Brown-of-Carbon ratio to limit the propagation, and actually, well, we have problems with those cross-sections. The uncertainty in cross-sections is very, very, very large, and we need to control that uncertainty in cross-sections. This is another work, recent work, which I was talking about by the Bone group, Reinert and Winkler, where they show actually the various parameterizations for the production of antiprotons coming from proton-proton collision. Okay, and finally, concluding remarks, I will flash that because I'm already very late. I thank you very much for your attention.
Thanks, Pierre, for a very comprehensive seminar. Any questions for Pierre?
Thank you, Pierre, for this very extensive review. I learned a lot. Of course, I knew very little from the start. So I have a comment on the question. The very interesting work you discussed on what I think is the direct dark matter particle detection, where you try to understand the velocity distribution function. So you referred to work by Thomas Lacroix.
Oui.
I don't know if you could, yeah, you just passed that here. So to invert the density into the distribution function of energies, you have to assume a very simple isotropic velocity distribution for one, or you can do it for Ostyakov-Merritt type of models. Okay, this is technical, but I think it's difficult to do in general.
Yeah.
And maybe they did it, I haven't read their paper.
They are writing the paper, actually. So the paper, which is either a draft of the paper, but yeah, they had, yeah, okay, go ahead.
But worse, when people do simulations, they find that there's a lot of clumps in the dark matter. So the clumps make the distribution function very noisy compared to your theoretical prediction. And so we don't know, whether the distribution function will have clumps where we are, where the Earth is, or not. And that will change the whole predicted rates of detection of dark matter. And then my question is, so how do you derive what you mentioned at the end, which I think is the key parameter, which is one of the key parameters, which is the propagation length of the cosmic rays? And
how do we derive that?
Because this will depend on the magnetic field.
Yeah.
And so the magnetic, and we have as far as I know, very little understanding of what the magnetic field is tangled or not in our Milky Way. And I'm not sure whether people are able to simulate this, adding the very important pulsars and maybe supernova remnants, which mess things up.
Okay, so the fine coarse, the fine grain structure of the magnetic field, well, might be not understood, but on general trends, the magnetic field, in fact, is composed of a regular field, and for half of the component, and a turbulent field for half of the other component. I think that, well, I don't remember really what is the structure of the regular field, but it's known, in fact. This is something which is known. And as regards actually the turbulent field, in fact, well, what matters is, in fact, well, it's turbulent, and so the cosmic rays diffuse on the knots of those turbulent field. There have been simulations actually even performed here by Martin Lemoine and Fabien Casse and Guy Pelletier, voilà. And so they've studied actually how the so it's difficult to work out and to compute ab initio. I agree with you, the normalization of the diffusion coefficient, but it's possible to see and to relate the way it depends on the energy to, in fact, the power law, in fact, for the delta B over B for the inhomogeneities of the magnetic field. The magnetic field has a spectrum, a turbulent spectrum, and so with a particular index. Okay, and so it's possible to relate the index, in fact, of that either it's Krigman turbulence or Kolmogorov turbulence, and so for those two things, for instance, for those two kind of turbulences, spectral indices, we have an energy spectral index for the diffusion coefficient, which is 1/3, a half for Krigman, and a third for Kolmogorov. So, okay, now to answer really the question on really do we need the details? We need, in fact, well, this depends on what you're dealing with. If you play with, for instance, positrons, we know that at high energy, the positrons come from the local region, then they come from far away, but then at very low energy, they are dominated by energy losses, so they tend to come from the local region. And so I agree with you that, well, that calculation of f of epsilon is complicated. In fact, well, so far I think, as far as I know, they computed just with the smooth component. Arguing from the fact that they could, if they have the cosmic rays coming from a region which is not too local, then that's fine, because then you have sort of an average, in fact, of that. And already with the smooth component, they had numerical problems. They had some infinities, and this depends on the cutoff, in fact, of their distribution of mass. But it's a very tricky thing. And they did that with the anisotropy velocity distribution. Okay.
So thanks, the talk was really great. There is a question that I always ask at this kind of talks. There is this discrepancy between the leptons measured by Fermi and AMS 02, and now Dumpy is more in agreement with Fermi than AMS. Because I remember when AMS came out, you know, they were like, oh, our energy calibration is better than Fermi, you shouldn't believe the flattening of the spectrum.
Thank you very much for asking that question.
Yeah, so I was wondering whether this is better understood now.
Okay. So when you read the Dampé paper, for instance, they say, well, we have discrepant result with AMS. And you can see, well, with increased statistics and improved understanding of the detector's performance, blah, 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 blah. So, well, when I have a student coming from his master thesis, and when he tells me, well, I have results I don't understand, but if I spend more time, I will understand that, I will tell him, yes, do it. So, no, so I'm a little bit, no, I'm not very, I'm not a nice guy here at that stage. But I think that, well, first of all, well, they have not completely understood their statistics. Dampé claims that. Dampé has very pristine results, pristine measurements, but they need to understand, in fact, their statistics. What I can tell you is that in AMS, well, they come from the particle physics community, and so they have tested their apparatus, just as Dampé, but I think they understand really the statistics. And so, personally, I would believe more AMS, unless they did a very big mistake. For Fermi, it's different, because it's difficult for them, actually. They're limited by their apparatus, because they have a few layers, in fact, and they might have events that are not totally confined, in fact, in the detectors. So this is understandable. For Dampé, they have a very nice detector, so maybe they have some things which they have missed, which is very easy in that kind of game.
But it's curious that Fermi and Dampé say exactly the same thing, right? I don't know how blind was this analysis. But
okay, so no, I have no explanation for that. No, definitely. I agree with you. Huh? I agree with you. Yeah.
If I can add something, the Galactic experiment. Yes. The Galactic experiment, which is a detector, which measures the same thing that Dampé and AMS, agrees completely with AMS. And only Dampé and Fermi is not dedicated to measure electrons and positrons.
You mentioned, bonjour, you mentioned the model of primordial black holes for dark matter, and you mentioned that it should give a contribution to the cosmic rays. I don't understand the process. You say that this is through evaporation, but...
Yes, only through evaporation, and for a very limited, in fact, range of masses.
But the evaporation is negligible for the LIGO black holes.
No, of course. No.
So
it's
which
a very
masses for the black holes?
I don't remember. 10 to the 13, 10 to the 14, 10 to the 15 grams or something like that. So that was one of the reasons why I was not that interested in black holes producing cosmic rays, because, well, those are very limited in mass, but who knows? And then you have really... you have limits, I guess, coming from the evaporation and production of gamma rays, in fact, from those evaporations.
So what is the process exactly?
Evaporation.
But the evaporation is through radiation, and then how do you produce...
You assume that you have some sort of a black body or gray body radiation, and at some temperature, well, as soon as the black hole shrinks, the smaller the mass, if I remember, the larger the temperature of the black hole, which is inversely proportional to its mass. And so you're going to produce, at the surface of the black hole, an emission, in fact, which is a thermal emission of all the possible beasts. So it's the inverse of the Big Bang, in fact, in that case.
One last question, maybe? Yeah.
the details, different methods, different, proxies that we can have from cosmic rays, antiparticles, and so on and so forth. Is there, I don't know if you have a plot which compare the constraint that we can take from cosmic ray from what we obtain from direct observation of dark matter.
Sorry, could you repeat? If I have a plot comparing what?
Is it possible to compare constraints which we obtain from cosmic ray?
Current
constraints on the mass of the dark matter with constraints that is obtained from direct observation of dark matter.
Oui. I don't have the plot here. I apologize, but yes. You can here in the let's see. For instance, in one of those plots here. Okay, so here are the constraints coming from cosmic rays. I think that, well, in that case, with the thermal cross-section, or at least, well, sorry, here is the, okay, so it's a limit on the cross-section. So I guess that here for an S-wave annihilation, I think that the cosmic microwave background constraints are better. For P-wave annihilation, it's vice versa. It's the other way around. Because for P-wave annihilation, in fact, in the primordial plasma, you have a velocity which is very small. If I'm Sylvia, if I'm not wrong, I speak under under Sylvia's control. So for a P-wave annihilation, so here the limits for S-wave basically are not as good as I would say the CMB constraint, as far as I remember. For P-wave, it's the other way around, because for P-wave, in fact, then you have a cross-section that depends on the velocity squared, and in the intergalactic medium, you have a velocity which is quite small at the time where, at the time of, well, on cosmological scales, when you have the injection of such energy, well, before recombination or okay, I don't remember, it's before or after recombination? During recombination, okay. Okay, and here for P-wave annihilation, the limits coming from cosmic ray positrons are better, much better. And we will be happy to show you the plot as soon as the paper is on archive.
And from direct observation, direct observation of dark matter?
So it doesn't measure the same cross section.
Because if I remember,
oui.
correctly, they have nowadays the constraint is very, very.
Oui, of course. Yeah. But it's not at all the same cross section, because for here we are probing the cross section with which, in fact, the WIMP annihilate with each other. It's the annihilation cross section. For direct detection, you have the interaction of a WIMP colliding on a nucleus. So it's not the same cross section. And this depends really on the model. I can tell you that they are somewhat related, but depending on the model, well, so of course, yes, you're right. The limits are very, very stringent, in fact. No, I agree. They are very stringent.
Okay, let's wrap up and thank you, Pierre.
Bon, merci. Thanks for your attention.